I am thankful to Roger for starting off with the application space, because this is the circuit code that will couple to the Empire code that he just presented to you. So Sandia has quite a bit of simulation codes and engineering codes, all of them having a very diverse set of requirements out of Trilinos, and this is definitely one of the most different, as it were. But this is the Xyce circuit simulation code that we develop using Trilinos. So I'm going to introduce circuit simulation, what it is, the equations it solves, what makes it different from, say, the application in the code that Roger just shared, and then talk about kind of the software architecture under Xyce, as well as some highlights of the capabilities and performance that we've achieved using Trilinos. Okay, so to start with, circuit simulation is a technique for verifying the design of electronic circuits prior to manufacture and deployment. So one of the reasons we care about circuits and their behavior is, you know, what Roger just introduced. We introduce and put circuits in very extreme circumstances, and we need to know that they function. And so it is necessary to simulate them in those circumstances. This is something that commercial tools are not designed to do. This is why Sandia develops a tool specifically to do this. So the other thing that there is of interest is not just the fact that we put them in the extreme environments, but that Sandia itself has its own microfab. So Sandia actually develops their own circuits and has their own process. So if you were here for Jonathan's talk, he mentioned CMOS 8. So CMOS 8 is a CMOS process that's actually developed at Sandia, and it needs to be qualified to radiation hardness. And so again, there's another reason why we develop our own tool to do this, because there are a lot of commercial tools, as one can imagine, that do circuit simulation. So why would we do it? So the fact of the matter is at least in the circuit simulation we develop at Sandia, we're interested in it also looking at it because of the fidelity that it's at. It sits in between a nice range of, say, if you go over to the right-hand side, you have device physics. Those are PDE, very expensive computations. And if you go over to the digital regime, you have very cheap, inexpensive computations that are determined on binary transition. But the problem is again, radiation physics sits in this inner regime where you need some kind of continuous behavior between the digital and the device physics. So in fact, there's a lot of digital components that we're interested in, but again, the environments require us to look at them in an analog simulation sense because we need to be able to determine how they behave. So the equations that govern this type of simulation are basically a network of devices that are coupled by a Kirchhoff's current and voltage laws. So that gives you this coupled set of differential algebraic equations that you see here at the bottom of the page. And there is a de facto industry standard for analog circuit simulation that's called Xyce. So again, there's a lot of commercial tools that do this, but they don't do it for the environments that we are most concerned about. Okay. So I've given you a lot of the background on why we care, at least in a Sandia sense, but to let you know a little bit more about the simulator itself, this is just a network DAEs. And so we could actually do other simulations, and we've done other simulations historically. We've done biological networks, neural networks, and power grids. So we've been involved in a lot of other efforts to use this type of simulator to do other types of analyses. So it does present a challenge because it is a single code base that needs to efficiently and seamlessly simulate codes that have a very wide range of sizes. So if you're looking at most, say, commercial off-the-shelf parts, you have maybe tens or hundreds of unknowns in those types of problems. If you're looking at, say, CMOS 8 ASIC, you're looking at tens to hundreds of millions of unknowns. It's a single code base that needs to span a very wide range and get performance at all sites. So it's also the reason why that Xyce provides both serial and parallel binaries, because the serial binaries, of course, are essential for very small problem sizes, and the parallel binaries are going to have special solution approaches for our very large types of simulations. Xyce is actually a open source code, so one could go to xyce.sandia.gov, or we have a GitHub that has our repository, and you can download Xyce and play with it. Yeah, and we can do that because, again, as a network simulator, anything that is sensitive in terms of models is kept inside of Sandia. So the basic model engine that can do anything is completely agnostic. So that's why we can open source this code. So at a high level, just want to give you an idea of the type of simulation and how this works. So for those who have familiarity with a PDE type of simulator, there's various stages in which, with the PDE simulator, you're going to mesh, and you're going to break it up over processors, and there's like these pre-work steps that you are going to do in order to do a simulation of anything that kind of comes from the PDE space. For circuits, you basically get a netlist. You get a file, it's an input deck, you don't know how big it is, how small it is. It's just handed to the binary, and you got to figure it out on the fly. So that makes it fun and a little bit challenging. So we have a substantial parsing phase that has to convert this, what we call a netlist, into the devices and the circuit connectivity or the topology. Then we have to, if it's in parallel and it's large enough, we're going to distribute those devices over the processors and try to determine how we break up this particular network. And then that determines global ordering and communication that we need to do. So, so that's up here. So from there, we basically have our simulation engine after you sort out what type of problem you're simulating, what type of analysis you're doing. Device evaluation, so evaluating, if you have resistor, inductor, capacitor, transistor, diode, whatever. That's done here at the nonlinear solver level. In the middle, we have this linear solve. It's because we use implicit methods. So we have a linear solve that does basically the linear solve right in the middle of that. And then there are advanced methods that we use within Trilinos for doing sampling, for doing polynomial chaos, or uncertainty quantification approaches, or optimization through roll. So those types of methods will then put this inside of an outer loop. So that's pretty much the structure of the simulation flow. So there's some challenges that we should point out that are what drive our use of Trilinos and the development of the tools or algorithms that we do in the code. So the first is the computational load balancing. So like I said, you basically solve the problem you're given on the fly. You don't know what it is beforehand. So we have to consider that in how we actually do our load balancing. So for smaller circuits, you're going to find that performing these device evaluations is going to dominate the simulation time. That's where the cost is. Actually, the linear solve is small, it's very cheap. But for larger circuits, we find that the linear system of equations is going to dominate this total simulation time. And so we have to go into much more trouble for, as systems get larger, as circuits get larger, into looking at how to make the linear solver less expensive. And so because of that, we employ a redistribution layer that you see here at the bottom to separate the load balancing strategies and the linear solver strategies, because they aren't equivalent. It's amazing that you'll find that in particular for, like, say, some transistor level devices, the equations that need to be evaluated are in the hundreds or thousands per one entry in a matrix. For a resistor, it's one equation. So your balancing is way off versus what your Jacobian, your matrix, ends up being. And so that's why we've put in these different load balancing schemes where we divide up the two, because we found that in practice that's necessary for Xyce to get the best scaling on both ends of this spectrum. Okay, so hierarchical connectivity. So network simulation codes do not have a PD. They're not based on a PD or a mesh. So your graph structures are going to be hierarchical. You're not dealing with the spatial topology, so you're dealing with, again, a network. So you have high connectivity nodes, likely come from, say, power sources. See here in the bottom right, you have a node count versus edge count, and you'll have not a lot of edges at a power node, but you have a huge node count. A lot of edges, but not a huge number of nodes. You have a power, basically element in there that is powering on all your devices. And so that is going to be a problem when it comes to parallelism, because you have a high communication node sitting in your network. And you'll also have higher communication nodes if you have buses or clocks that are running across, say, circuitry. So it's important to, if you can, remove any high connectivity nodes in these circuits, because they will cause all kinds of bottlenecks in terms of getting parallel performance. So when it comes to actually solving the linear system in the middle, that is an area where the matrix itself, as you can see, there's a SPI graph on the left-hand side. You can see kind of this heterogeneous structure. We have found, unfortunately, that direct solvers provide the robustness that we often need, as opposed to iterative methods, which obviously provide scalability, but have been difficult to come by efficient preconditioners. And I should say at this point that if you look at a network simulator, or you think about a network simulator, it can produce any kind of graph. Any kind of graph. So you could actually, if you look at a transmission line or a cable, that looks like a 2D, Laplacian. That's the graph you get. That's a good day. That's a great day. I love that day. But I don't get that day very often. I get things that are nasty, and that's often what we have to solve, which is why we've been spending a little bit more time recently developing direct solvers in order to do this more efficiently. So, that meant to do that there. So, okay, moving on to Xyce's use of Trilinos. So, Xyce was one of the, as opposed to Empire. Empire kind of was born and bred in the new Petra stack. I'm excited for them. I'm happy. But Xyce was started in 1999. So it was one of the first applications at Sandia that was using Trilinos, that fully embodied the use of Trilinos. And so historically, the Xyce simulation tool used quite a bit of the Trilinos solver stack. So this is to show, this is what our usage of the pre-Trilinos 17 stack looks like, right? We have ePetra, Tefos at the bottom, Zoltan, and Seropia for our balancing. We have our solvers in the middle. And then nonlinear solver, homotopy methods are very important. Optimization and the stochastic Galerkin type approaches at the top. So over the course of the last 2-3 years, I have been working to transition this solver stack to tPetra. Now, the one thing that has helped me is this lovely abstract interface that sits in the middle here between the Xyce code and the Petra code, because Xyce is still very much used at the labs to do its ND qualification work. So, driving the car and replacing the engine at the same time is really not something one likes to do. So, this interface helps try to separate out this transition. And so we have been going through that for the last couple of years. And so to, crib off of a lovely graphic in the new paper, because I didn't have to make it, that's always helpful. This is in the new T-Petra stack. We are going to now develop, or we are developing interfaces between Cocos, Tefos, T-Petra, and that interface, our solvers will be in that space, and then the nonlinear solvers and optimization, uncertainty quantification are going to be in that space. So, but the nice thing is that they can be written to this abstract interface, and that is something that we've been working through. So yeah, from here I was going to, as part of the talk, go into fun lessons I've learned, right? And this is the fun part of the talk, where I get to do therapy in front of everybody. You're all gonna love it. It's gonna be great. So, yeah. T-Petra transition effort. Okay, so we were one of the first application codes, and we really did embody the use of Trilinos in our design, which is good and bad, right? So it means that the first thing you have to do is some cleanup, right? You gotta get in there with your mop and bucket and figure out what you've done wrong. And Xyce has done a lot wrong, so I'm not here to like throw shade on T-Petra. There's a lot wrong. We're gonna deal with that. Yeah, our abstract interfaces look a lot like T-Petra. Okay, I think that's all right. T-Petra is a little different, but that might be okay. Rampant use of raw pointers, followed by an inelegant use of smart pointers. Yeah, that was fun. That's a lot of fun right there. Can't say that's entirely taken care of, but I think I've got more of a handle on that now. So Xyce has a lot of direct access to the matrix and vector entries in the device model. So we hand the pointer to the memory to our device models for matrix and vector loading. So yeah, I mean, that feels wrong, but the challenge is, going back to what I was saying before, you have the same code base solving very small problems all the way through very large problems. For the very small problems, you can't really put up with many layers of indirection and getting yourself loaded into a matrix or a vector. So yeah, ubiquitous use of copy semantics in T-Petra for map graph objects. So T-Petra allowed the use of an argument where you could say copy or view. And you could hand it, for this it's a graph, you could hand it a map. If it's a matrix, you handed it or a graph or a map. And you could tell it whether you wanted it to copy that object or view that object. Okay, T-Petra says it's a ref count pointer, we're just viewing this thing. Yeah, Xyce liked a lot of copies, turned out. So if you just went through and hack and slash, ooh, okay, careful, hack and slashed it through the code, and you just put views everywhere and just gave it ref count pointers, there was seg faults a go-go, because you were creating a graph or a map, and then it went away, and you gave a pointer, and no. So that was a little bit of work. We had a lot of dynamic creation of graph and matrix objects, unnecessarily so, because actually once that network is determined, it's static, so that's not needed. So we cleaned that up. That was good. And then we relied on a lot of supporting tools provided by T-Petra ext. That's my fairy. The fairy was, I needed help. So, singleton filtering, partitioning interfaces, remapping utilities, all the things that sat in that two-layer of redistribution that I showed a couple slides ago, all these tools sat in that redistribution layer. And so I needed to ask for help. Right, Kurt?
Yeah.
I asked for help. Okay. He's so happy I did. Okay, so I got through that, and then I thought, okay, I'm ready. Let's go. I can do this. You know, everybody loves ripping out the engine. So next step. All right, hammers and nails. Let's how did this go? Okay, so transitioning, there were helpful things. Many of the interfaces were Petra-esque, yay. So what I thought was kind of and in fact, I mean, props to the T-Petra team. I think they went through great pains to keep some of the interfaces that were more ePetra-esque and passing raw pointers and things than I expected, right? There was a lot more effort in doing that, in making the transition for people easy. So I did appreciate that. Unexpected challenges. Oh, the resume fill. Yeah, so Xyce, at least at this point, is running on a serial Cocos node. I have not, you know, for various reasons that I think are maybe evident, and what I've already said, we are not going to GPUs anytime soon until several things are sorted out. So the resume fill I was not prepared for, having to put it into as many places that I needed to, because we have cases, and we'll get to some of those cases, when our matrix loading is a multi-stage process. And so knowing when to be inserting this and when not was a little bit. And it wasn't entirely clear. Sometimes I wouldn't put it, and everything, it would run, and then there was nothing in my matrix. Oh, okay, that's fun. So let's see, obtaining a pointer to the underlying memory to pass to the device models, which I know is bad. I mean, shame on me. But required interacting with Cocos objects, which were disguised by a typedef. I love typedefs. God, they're great. What is that? What is that thing I'm messing with? I have no idea. It's a typedef. So that was, sometimes I had to figure out things the hard way, but I got that. Let's see. Capabilities for block analysis methods, again, we'll get into this a little bit more, may not be compatible with the T-Petra design. Lots of crying there. Because there's a lot of bespoke things that sit inside of Xyce to do frequency domain analysis, which is important. And they are very bespoke things. And getting them to work with T-Petra right now is a bit kludgy. I think there's a better way. I'm sure there's a better way than what I'm doing, but haven't found it yet. Okay, yeah, this one is a more recent one when I was getting some behaviors, my final tests passing. There are some non-member helper functions that kind of do all-in-one to create new objects for importing and exporting data, but I had mixed results there. Sometimes the object had a very weird domain map, and sometimes if I tried to reuse the object, it seg faulted. So again, I intend on making an example and submitting that, but I kind of, okay, I'll get back to that. So, all right, but it sounds like pain. The challenge is that what Trilinos has done the most for Xyce is enabling the development of linear solvers. And so this is an opportunity where we have really used solvers or develop solvers within the Trilinos framework. And so to give some examples of these custom solvers, so BTF, which is behind the KLU direct sparse solver, we could use it, have used it to create preconditioned iterative methods for CMOS memory circuits. These are older designs, so they actually that had less of a irreducible block than what Jonathan showed. So you could actually get them to partition into, say, 4 blocks like that. That's much more friendly. And so those solvers actually allowed us to do some memory circuits for CMOS. We developed this as a custom approach through Trilinos. This is kind of, again, piggybacking on what Jonathan was talking about with the Shiloh-Basker improvement. We developed that, again, for various types of CMOS circuits. And it got extended for the use of CMOS 8, for which we got a mention in the High Performance Computing Annual Report for this work. And then using, actually I'll go back for a second, there is a templated LU solver based on a traits mechanism sitting in Trilinos. And that is actually what we use to develop a bespoke frequency domain simulator in Xyce. And so if you're using harmonic balance in Xyce, basically you're taking that set of DAEs, you're going to do a Fourier expansion of x of t and b of t, so the forcing term in the solution, and then you get this new blocked system. And then you have to, inside of that, evaluate q of x, f of x, but our devices are time domain models, so you cannot evaluate them in the frequency domain unless they're linear. Yes, you can do that, but they're mostly nonlinear. So then you have to basically insert a discrete Fourier transform in order to get this block Jacobian system. And most people don't want to solve it. They, in general, like to use iterative approaches and maybe a block Jacobian. But we actually leveraged a Mesos solver, the Basker templated solver, to create a direct solve, which was basically developed using this sparsity structure. What you do is you take the original sparsity structure of the Jacobian, and each entry is now a block. But if that device is linear, that block is actually a diagonal. So you can actually have a very structured solve. So we actually created a nice structured solve using that. And that was necessary because for highly nonlinear circuits, actually preconditioners and iterative methods for harmonic balance are hard to get as well. So we, bless you. So, like I said, dense blocks are created when voltage nodes are connected to nonlinear devices. Otherwise, you get diagonal blocks. The nice thing is the templated nature. We can actually create this new solver, which has been really, really helpful for us to employ our harmonic balance approach and get it into our customers' use. And this is a great jumping off point. Because there's a lot of opportunities here, I think, for COCOS to actually help improve the solver even more. But it is just kind of, those are some examples of areas where Trilinos has been the most effective in working with Xyce, because we interact with the team and it's a very fruitful framework and teaming that happens. We develop new solvers and new approaches and things like this. And for a code like Xyce that is so much different than a PDE code, we need these kinds of engagements in order to develop a solution approach for our customers. So I think with that, that is my last slide.
Thank you. We're running long, but if we had a question or two, I would, let's see, who's up next? Marco. Yep. Okay, so when you're coming up, why don't we go ahead and field a question?
Yeah, great talk. I had a question on,
Sure.
like, you initially mentioned something about coupling Xyce with Empire for future plasma circuit simulation.
Yes.
Do you have any experience with, like, how was your experience coupling that?
So how is my experience coupling that? So I have not been the person to do that one, but the how do I say, what they're coupling to right now is very simple linear circuits, I know, and so by far Xyce is not the hard part of that problem. The Empire part is still the harder part of that problem. So, yeah. Okay.
Alrighty, let's thank Heidi again.
Hey.
Did you want that?
No.